All right, we're up and running. I think I've got the entire board captured on camera. Do I? I think so. All right, so this is going to be labeled discussion 1. And we are going to start with something that probably was established thousands of years ago in terms of math. And then we're going to move forward to the 1600s when I think Newton, using a square, formulated his understanding of calculus. Okay, and it's certainly evolved since then as well and continues to evolve. All right, but my experience with calculus was, I guess, college, my freshman year. I took a calculus course, and then my spring term, I think I started second year calculus, and I think I dropped out. Right? I don't think I ever told the registrar, so I just, was a little bit of a rebellion in my life at that stage. Had to work through some things, but that's another story. And then I started Algebra 1 at Eagle Brook. And again, didn't know any math, so I've learned it the way you're learning it. Okay, so I'm not learning it and then coming back and teaching it. I'm teaching it as an adult learner, which has its pluses and minuses. So I'm going to call these discussions the geometry of change. I'm going to use a cubic as an example. And what I'm proposing to you is that there's a lot going on here that doesn't necessarily come immediately from a quick glance. That it really takes some, what can I glean from what I'm studying? And that's what it means to have a critical eye, to look at something critically, to really look at it more deeply, and then to see what kinds of things come from that analysis. That's what I'm hoping we do here. All right, so this will be the first discussion that we have. Have you been timing, Nabil?
Yeah.
Okay, you tell me when 10 minutes is up, and I don't care if I'm in mid-sentence. That's it for the day.
Yes.
All right, so cubics, I think there's a big kind of clue as to what we're going to look at here. Cubes. All right, so I've drawn a few. Obviously, could continue drawing in that direction, but ran out of board space, and could continue in this direction, but running out of board space. So, tell me all the things you see up there about these cubes. Little descriptors would be helpful. What are you seeing? Anything at all?
Lines.
Lines, yes. So we can use a one-dimensional line, and if we do enough of them, we can draw something that we call cubes. Anything particular about these cubes? Are all cubes drawn like that?
Equal side length.
Oh, so we have equal side length cubes. How about we call that a perfect cube? Okay, because we can certainly draw cubes with different lengths, yes? And trust me, we're going to. Right? But right now, we're looking at perfect cubes. And I don't know, I think we usually use the term volume, don't we? When we talk about the space contained by those rectangles, 6 of them that we've drawn. Well, they're special rectangles, aren't they? They're actually squares. Yeah, 6 squares put together makes a nice shape that we call a cube. Right? And I guess we associate numerical volume with those cubes. Right? So a -3, -3, -3 gives us a volume of -27. I don't know enough about science if that's an exact, seems to me that negative volume really doesn't exist, I guess, but numerical, yeah, we can talk about the numerical volume. And that's all I can say about that, is that's what you get if you multiply -3 times -3 times -3. And then, of course, we get, that volume and that volume, and that volume's hard to see. And that volume and that volume and that volume. What would you tell me about the volumes? They're what? Yeah, they came from doing something to the third power. That's a shortcut to doing -3 times -3 times -3. So -3 cubed, I guess, we've memorized it because we've done it so much. That's helpful. That probably happened after somebody drew these and thought about them for a while. Right? And we're kind of going up the historical ladder, aren't we? What else can you tell me about these numbers, how they are related to each other? What would you say those numbers are doing? Well, if I went from a 2 to a 5, what would you say just happened?
I'd agree.
Okay, what else? My second number is what?
Larger.
Larger than the first. How about those numbers?
They're growing.
They're certainly getting bigger, right? Whereas the tricky concept is the numbers are getting bigger, but the space that we're trying to describe,
It's really small.
the magnitude seems to be smaller, right? Yeah. Now, you've been studying trig this term, right? And the reason I'm doing this is I'm trying to give you a sense of the pre-calculus skills necessary to prepare you for your next level of study. All right, because even though I had some very wonderful colleagues teaching here, and even at GCC, when I took these 4 calculus classes I took, right? And I taught it for 3 years before I made any real connections. And I don't think you can make connections unless you study the geometry of what the origins come from, which is what we're doing now. In my Algebra 2 classes, I always teach the unit circle. Because guess what people bomb at the pre-calculus level? The unit circle. If you don't get it in 4 or 5 days, you're done because you move on to something else, right? And I want to make sure people are successful at the next level. So I try to give them the unit circle so that when they get there, if you can do the unit circle correctly, you can pretty much dive into all the other topics. But if you can't do it correctly, you're got to be careful what I say because I'm going to post this. You're in a reality comedy show there. Yeah, that creek thing. What time do I have left, Nabil? Are you even keeping track? How much time do I have?
Approximately.
4 minutes, okay. So in trigonometry, I've been trying to say you do this to get that, or you do that to get that, yes? Do you remember what those 2 things are? Angle to ratio, ratio to angle. That's basically what you're doing. You know, with all these sine x, cosine inverse of x, right? X either stands for a ratio or an angle with the language associated with it. Well, calculus is either I give you a rate and you give me an amount, or I give you an amount and you give me a rate. Do we have rate of change here? Yeah, we do. The volumes are changing, right? And I guess we want to try to answer at the calculus level at what rate? Well, I guess that means we got to talk about how do we measure rates of change? I guess we got to think about that more deeply. How do we measure rates of change? Been doing it. Wouldn't it be nice to know when you're doing it and why? Huh? Well, exponents certainly give us various x to the 1, x to the 2, x to the 3. Those are all changing at different rates, that's for sure. And now we're going to try to get a tool that explains how. Like the virus is out there, right? Right. And we have these kinds of graphs. Right? Something like that. Right? And what are those graphs communicating to you? Rate of transmission. Notice the word rate. Okay, where's the greatest rate? I guess here. And that happened when? Omicron, right? The variant Omicron. Right. And then we had another high rate Christmas last year, right? Because people are getting together and indoors. Right. So what's the difference between a rate on this side of the curve and a rate on that side? Yeah, we want to bring in words like increasing and decreasing, right? And it's increasing here, isn't it? Increasing there?
Yes.
All right. And if we saw that increase, we might, as people talking about public policy, wouldn't we get concerned? Ooh, the rate's going up. If the rate's going up, then what do we know? More people are going to get sick, right? So aren't these really important issues as to at what rate is it increasing, right? Because then we make public policy. So we want to devise some terms and some ways to do that. And that's what these discussions are going to be about. right? And we want to get some of the symbols that go with that discussion to be somewhat recognizable, because that was the problem that I had teaching it and studying it. You're gonna see that term more than anywhere, than anything else in a calculus test. You're gonna see that term right there. Nobody ever explained it.
I'm done.
Done. Okay, rest of the period's yours. We pick up from here tomorrow. And we'll see if we can march our way towards the first fundamental theorem of calculus.